So I'm really pleased to introduce Petar. So Petar is one of those geniuses that excel at maths. And he was born in Serbia and did his undergrad at Cambridge University in the computer lab. And then immediately, after just doing a bachelor's, after 3 years, immediately went on to do a PhD. And during his PhD, he's doing research in different machine learning techniques, including some deep learning models. And today he's going to talk to us about deep learning. And I was having a chat with Petar, and I was saying, hey, you know, you only have 25 minutes. Is that okay? Because everyone else has 25 minutes and 5 minutes of Q&A. And Petar was like, no way, I need more, I want a double slot. I was like, really? I was like, yes. And I, okay, fine. So Petar is going to talk for around 40 minutes on deep learning, but you know, it's a very hot topic which deserves a lot of attention. So hopefully everyone will learn something from it. So over to you, Petar.
That's totally not how that happened. But yeah, thank you all for the fine introduction. So hi everyone, my name is Petar, and today I will be talking to you about, well, the history of deep learning and how it became what it is today, and maybe some aspects of where it's going. So I will give you an introduction into how neural networks normally operate, and I will perhaps preview a few of their interesting variations and applications. And I'd like to highlight that this is not a deep learning tutorial. For those of you attending the workshops on Sunday, I will be giving a more proper neural networks and deep learning workshop. And just a disclaimer for any researchers in the room, I'm bound to upset some of you because I'm going to mention which paper are the most influential in my opinion. And this is heavily biased by the kinds of problems I'm solving. So you can put any other deep learning researcher in my spot, and he might be giving you a completely different overview of what the most important works of deep learning are. And there's so many papers that none of us can really keep track anymore. So on that note, let's begin. Let me give you a motivating example to kind of kickstart this whole neural networks deep learning process. Which character do you see here? It's not a trick question. Yeah, so you see a bunch of examples of an A character. But if I were to ask you, how did you conclude that this was an A? Or more specifically, would you be able to give me a set of rules for me to determine that I'm looking at an A? Presumably that would be quite hard, but it was quite easy for you to say that you were looking at an A. So if I asked you to write a program that would be able to recognize characters from arbitrary images, this is a standard image classification data set, you'd probably think that writing a program would be quite hard. So although the previous task was probably quite simple to you, turning your thought process into a coherent program would probably be quite hard. And unlike a program that just blindly executes pre-programmed instructions, you've been exposed to a lot of A characters in your lifetime, and you have a rough idea of what makes an A, even though you cannot really quantify it. And the desire to make systems like this that are able to learn from past experiences is pretty much the essence of machine learning. And how many systems like that do we know from nature? Well, we know only one. And this one system is, oh, you can see it here. So we should look just briefly at the brain. We know that different parts of the brain specialize in different tasks, and there's increasing evidence that the brain actually learns from being exposed to data and is not pre-programmed to behave in a certain way at all. And the way in which we know this is, unfortunately, usually through studying brain defects, brain damage, and stuff like that. So what happens when you, for example, reroute visual inputs of baby ferrets into the region that's normally taught to process sound, well, it ends up being specializing as a visual region. And vice versa. If you feed auditory inputs into a part of the brain normally associated with vision, that part ends up specializing to process sound. So there seem to be no major biological differences in learning how to process different kinds of input. So the brain probably has some kind of a general learning algorithm that is capable to adapt to a wide range of inputs. And we'd very much like to capture this algorithm. So here's what a real neuron looks like. Each neuron processes some inputs that are fed from other neurons, and through its extensions called dendrites, it computes something based on what it's seen in these inputs, and then it sends some result across through its axon to be fed into other neurons for processing. So there is the simple way of connecting outputs of some neurons to inputs of other neurons and passing some electrical signals and hopefully computing something useful. So the first attempt to translate this into a computational model is really simple. So I have some inputs, some things that I care about, some things that specify my problem. And I'm going to assign some importances to each one of my inputs. So these things we will usually call weights. Weight 1, weight 2, weight 10. And I'm going to, in the simplest possible scenario, I'm just going to multiply each one of my inputs. These will be usually real numbers with these importances, which are also real numbers. And there might be a special bias factor, which allows me to shift left and right. And I'm going to say if this whole combination of inputs exceeds a threshold, I'm going to send an impulse. So I'm going to return a 1. Or if it's less than this threshold, I'm going to return a 0. So we've built a really simple binary classifier, a really simple model that's capable of saying yes or no. And this is the perceptron that was popularized by Rosenblatt in 1957. So obviously, what defines the way in which a neuron learns, in which a neuron behaves, is which parameters it has and how they respond to different data. So we need to find a way to learn them from past experiences, from known input-output examples. And one popular technique for doing this, as you might know, is gradient descent. So if we have some way of quantifying the error that the network makes on our training examples, which is usually a differentiable loss function, then we can take the gradient of this loss function with respect to the weights and update our weights slowly in the direction of this gradient and hope that we reach good results. And we also have this step parameter which controls how much we move in the direction of the gradient. It's called the learning rate, and properly choosing it is critical. We will touch upon this again later on. And this is the very crude illustration of what goes on with gradient descent. Your weights initially might be causing a huge amount of error on your training set, but you take small steps in the direction of the gradient, and eventually you reach a point where the error that your network makes on your training set is really small. Okay, so the fundamental issue for applying gradient descent to the model that I just shown you is you have to be able to take gradients, but because the network just says 0 or 1, it's not a differentiable function, it's a step function. So we cannot really take a derivative of what the network is doing. So the solution to this was to use the smooth variant of the step function called the logistic sigmoid. And this will give you a value between 0 and 1, which you can interpret as the probability of saying yes. And you can classify depending on whether this number is greater or less than a half. And this can be generalized if you want to not just say yes, no, but also say class 1, class 2, class 3, class k. You can create a vector of k different importances and apply a more generalized function called the softmax function, which is now ubiquitously used across a variety of deep learning applications. So just to illustrate how this sigmoid function smooths a step function, our previous neuron model kind of just either said 0 or it said 1, depending on whether its output was above or below a certain threshold. And the logistic sigmoid function kind of smooths it out depending on the parameter. So this now we can take a derivative of, and we can actually use it to efficiently train. Okay, so now if we define a suitable loss function, we can train the neuron using gradient descent. If we don't know anything specific about our problem, so we just have some outputs and we want to see if our network is producing comparable outputs, and these are numbers, the simplest thing we can do is just feed our input into the network, compute some outputs, and compare it to the expected output with the squared error. So we take the output of the network, we take the expected output, and we take the square of the difference of the two as our loss function that we want to optimize. We can take some more sophisticated variants of the loss function. If we know we're using logistic functions or the softmax, we can interpret things as probabilities, and from probability and information theory, we can take the cross-entropy loss, which is currently the pretty much the ubiquitously used loss function for probabilistic classification. And some of you may recognize the setup so far with just a single neuron, or well, a single layer of neurons as logistic regression. Okay. So, when we have a single perceptron, we are computing a linear combination of our inputs and making a decision based on that. That means that if you visualize your inputs in some space and you want to visualize your rule for deciding which class the example should go to, then your rule has to be a linear rule. So if you have data that's distributed like this, then it's very simple to make a linear rule. You just draw a line like this, and it nicely separates the two examples. But for many years, there was an example that killed off neural network research, the so-called XOR problem, with data that is still very clearly separable, but there is no way to draw a line that separates the pluses and the circles. So no matter how you draw a line, you're not going to be able to split these two. So in order to be able to advance further, we had to invent ways to insert nonlinear decision boundaries into the problem. So this kind of takes us from a notion of a single neuron to a notion of a neural network. We can just take a bunch of neurons and feed outputs of some neurons to inputs of other neurons. And if in the middle we apply some nonlinear functions, we can suddenly specify nonlinear decision boundaries. So this has the properties that we care about. Typically, we will organize these neural networks in a sequence of layers, such that each layer processes only the outputs of its preceding layer. So it's a step-by-step kind of computation. And the most powerful, the most potent architecture that works like this is the multilayer perceptron, where all the neurons in a single hidden layer are connected to all the neurons in the previous layer. So it has unrestricted connectivity, and it's, in theory, the most powerful neural network model you can have. If you have enough data, this model will always behave the best. All the models that came after it are kind of specializations in the sense that if this network had enough data, it could learn to behave like a convolutional network if it was looking at images, for example. So that's why we want to kind of pay special attention to this model, even though it might not be what's kind of the most popular model right now. And we've known of variants of this model since the 1960s, actually. And everything that modern deep learning is doing is just specialized versions of these multilayer perceptra. So stacking neurons in this manner will also preserve differentiability. So we can use gradient descent again. We can take a gradient of the loss function with respect to any of the intermediate weights of any of these neurons. So we can use the same algorithm again. But initially, it was quite inefficient to compute these gradients, and this also held back neural network research for many years, until 1985, when Rumelhart, Hinton, and Williams invented the backpropagation algorithm, which I'm sure pretty much all of you have heard of, at least. And the idea of the backpropagation algorithm is quite simple, actually. So we feed our input to the network, we compute some output, we compare it to the expected output, compute the loss function, take the gradient of the loss function, and we can compute it for the weights of the output neuron directly and actually efficiently propagate it backwards using the chain rule. And that revolutionized, once again, neural networks research because it allowed us to train very deep networks computationally efficiently. There were still some numerical inefficiencies, but we'll get to those a bit later. So gradient descent will optimize all of my weights and biases in the network. But there are a lot of things that I need to specify before I even start training the network. So I need to say how many hidden layers I have, how many neurons I have in each hidden layer, what are the activation functions of these neurons, how many times I apply gradient descent, what's my learning rate, so on and so forth. And because we have to specify them before training starts, we call them hyperparameters rather than just parameters. And optimizing them is still a very difficult and open problem. In most cases, you cannot really do better than just separating out some of your training data and trying out many different combinations of the hyperparameters and seeing what works best. And in particular, I'd like to focus now on the number of hidden layers in the network, or the network's depth. So what do you think? How many hidden layers do I need to be able to, in theory, learn any function that I care about? Just one, yes. And this was known since 1989, Savenko's theorem, where it was shown that a neural network with a single hidden layer that only had sigmoid activations was capable of learning any bounded continuous real function. So, and this kind of motivates why deep learning is called deep learning, because essentially, whenever you have more than one hidden layer, you're using more than, in theory, you really need. But the problem is, this theorem just proves that it's possible. It doesn't tell you how big this layer needs to be, and it doesn't give you a training algorithm. So in practice, the idea is not to go wide, it's to go deep. So whenever we have more than one hidden layer, we have a deep neural network, and today's state-of-the-art networks often have over 150 layers. Okay, so I have skipped the most interesting slide, which kind of contrasts the way machine learning used to be done prior to the boom of deep learning and the way it's done now. So previously, people used to analyze things much, much more rigorously, whereas nowadays, the trend just seems to be if you put enough layers and appropriate regularizers, your networks will simply just work, and you can stack infinitely many layers, and things will usually just kind of work out the way you want. Obviously, this is a joke, but there are some really fundamental aspects of deep learning that we really need to address right now from an intuition standpoint. So, out of the people in the room, who knows what these two events are referring to? Right. So, okay, so about 50% of you. So on the left-hand side, we have the famous chess match of Garry Kasparov against Deep Blue in the 90s, which was one of the first great success stories of artificial intelligence in game playing, when a chess agent successfully defeated a human grandmaster. And on the right-hand side, you have a shot of Lee Sedol while he was playing the famous match against AlphaGo a few years ago, where, once again, for the first time, a neural network was capable of defeating the human Go champion. And these two events represent two different approaches to machine learning in general. The main idea of these two is roughly the same. You assume that a grandmaster is capable of thinking k steps ahead, and if you can then create a methodology that is capable of thinking k prime steps ahead, which is more than k, you can defeat a grandmaster. And the difference is in the way this is done. Deep Blue exploits the fact that chess is not that dense to actually exhaustively enumerate all the possible moves that the algorithm can take, whereas AlphaGo discards a lot of moves that it thinks are highly unlikely. But there is one key issue. You can never really, especially not early on in the game, you cannot really evaluate all the way down to the end of the game. So you have to stop exploring the tree at some point. And how do you determine the advantage that player one has at this point? So you have to you've reached some state of the board, and you have to say, what's the score of this board? How much is player one in advantage right now? And the way Deep Blue did it is they gathered a team of chess experts, and they defined a handcrafted function which takes the state of the board and gives you a real number, which tells you what this advantage is. Whereas AlphaGo feeds the raw board into a deep neural network and lets the network learn the advantage function by itself. So this highlights an important paradigm shift that deep learning has brought about. Historically, machine learning problems were tackled by first defining a set of features for the problem that you care about, and then giving them into traditional shallow models. And many scientists built entire PhDs focusing on features of interest for one particular problem. And this means that your generalizability is usually quite small, often zero. So with deep learning, the network learns by itself what the interesting features are directly from raw data. And this means that you have this unified algorithm that can be applied across a variety of areas. And for the first time, it truly connected researchers from a variety of different areas, like natural language processing, computer vision, and so on. And it also implies that assuming that your problem has a sufficiently large data set and you're capable of working with deep neural networks, you can usually readily apply your knowledge to create state-of-the-art models in virtually any domain. Okay. So as the inputs go through the layers of the network captures more and more complex features of the inputs. And it would be extremely valuable if we can reason about what these representations are. And usually you get the best kinds of visualizations when you work with image models. So now I will give you a brief introduction into what we need to talk about image models, in particular convolutional neural networks. So thus far I've talked about multilayer perceptrons, which typically actually fail when you give them image data sets, and this is because they have lots of pixels, and if you treat each of them as an independent input, that gives you a lot of parameters that need to go into every neuron of your first hidden layer. And as images becomes larger, this quickly deteriorates. So the key idea is actually quite simple. Make the images smaller, make them small enough, and then you can treat each pixel independently. But obviously, when you make them smaller, you lose a lot of important information straight away. So you would ideally want to first extract some useful information from the image and then make them smaller. And you want to do this cheaply. You don't want to waste a lot of parameters doing this. And you can exploit the fact that in an image, the inputs are not truly independent, right? So each pixel is usually heavily related to the pixels surrounding it and heavily unrelated to the pixels on the other side of the image. So you exploit the spatial structure in an image, and luckily we already knew about really cheap ways of exploiting spatial structure from images, and that is the convolution operator. In this case, with only 9 parameters, I'm able to extract several interesting edges out of this image, which is actually quite important because 95% of the information is contained within the edges. This is why when you see a sketch of a person, you can usually always with certainty recognize who this person is supposed to be, even though all you're seeing is a few blobs. So this is why edges are actually quite important, and if we can extract them efficiently, then that's already a great step in the right direction. And the convolution operator is quite simple. We take a very small matrix. In modern deep learning, usually they're just 3 by 3 matrices. You put this matrix of real numbers in all possible ways on top of your image, and you record sums of element-wise products. This is the mathematical expression. I will give you a really nice illustration in just one slide. And the operator exploits structure, because in this formula, only adjacent, a really small neighborhood of each pixel is located in this formula, which means the convolution operator completely discards things that are across the image from each other. And because all you're doing is taking your input, multiplying with parameters and adding it, you're just pretty much doing just a specialized version of a multilayer perceptron, meaning you can train exactly the same way as you trained before. Start with a random kernel, K, and let the network learn the optimal one by itself through backpropagation. And this is the illustration that I talked to you about. So we have this kernel, and it's designed to detect a particular pattern in our image, and we overlay it. We just kind of slide it across the image, and we cross-multiply all the positions that match up, and we record the result in a pixel of the corresponding image. And this is a very cheap way. So know that now we just have 9 parameters, and we're capable of extracting a complex feature out of our image. And now I've talked about how to extract the features. I didn't talk about how to make the images smaller, which is what we eventually need to do. So what happens is convolutions will light up, so the values will become higher when they detect a particular feature in an image. So if we want to summarize a particular region of an image based on how much it's activated by this filter, we should just it's kind of sensible to take the maximum value, because it tells you what's the most of this pattern I've been able to detect in this small region of the image. And this is the inspiration behind the 2x2 max pool operation, where we just split the image into 2x2 disjoint squares, and we just record the maximum from each of those. And this is a nice way to rapidly downsample the image and prepare it for processing by a fully connected network. Okay? And the rough rule of thumb is, as you go down the path of a convolutional neural network, every time you downsample, your height is halved and your width is halved, which gives you more space for depth, which means you can compute more features than before, and you just kind of end up stacking these convolutional and pooling layers one after the other until the images are very small, usually like 8 by 8 or so, and you can take every single pixel as an independent neuron for a multi-layer perceptron. So this is the most standard typical convolutional neural network architecture that you might be able to see in literature. And they're by no means a new idea. We've known about them since the late 1970s, but Jan LeCun popularized them in 1989 when he used them to classify handwritten digits. And this is the standard MNIST dataset benchmark. If you go on YouTube, you should be able to find this video of the demo from 1993, where they show some digits to the computer, and the computer is in real time determining which digits it's looking at. It's a really cool video. I recommend looking at it at Jan's YouTube channel. And now that I've told you a little bit about how these convolutional networks work, we can actually talk about how to make sense of what they're doing. So typically, we can look at what these kernels are, but as they're small, gaining useful information from them becomes usually difficult after the first layer. But the first layer already reveals something magical. I've started with random kernels and ended up with something like this. So to any of you in the room who have done signal processing, this should immediately strike you as an edge detector or a variety of different edge detectors. So the network has learned by itself to detect edges in the image. It's learned by itself without knowing up front that it's looking at photos that edges are important. It's learned that edges are important just by looking at the data. So this is something truly magical about how these convolutional neural networks operate. And let's look at what happens when I feed something through a convolutional neural network. So I take this photo of a cat, and I want to classify it as a cat and not as a dog. And after it goes through a few of these convolutional layers, in a very shallow layer, now unfortunately this is not very bright, but you can see that after the first layer we can already detect some really crude elements of this image. We can, for example, isolate the background from the cat, or we can isolate the cat from the background. Very simple stuff we can do after a few convolutional layers. If we go a little bit deeper, now this might be a little bit harder to see, but we're able to extract some really, really complex level features that we might not even be able to reason about, but they might be able to tell us as to whether I'm actually looking at a cat. So we can, for example, here you might see high activations around the cat's eyes. So a cat's eyes is a very distinctive feature, or high levels of activation around the cat's ears. So things that kind of we would see as being distinctive of a cat, we can see as activations in a very deep layer of a convolutional network. And as it all goes down at the end, we have a huge, well, this is from a huge classification problem with 1,000 classes, and we can see it assigns a really high probability. Well, we don't have labels, but take my word for it, this is a cat. And it assigns a probability of about above 25% that this is a cat, which is actually quite huge because we're looking at 1,000 classes. So a probability of 25 is actually quite big. The network is quite confident that it's looking at a cat. Okay. Right, so this was a very brief introduction into image models. Now I will give you a brief introduction into sequential models. Now we're looking at a different kind of problem. A problem where our input is a sequence. And there's some number of steps in the sequence, and at each step we have some features. This is very directly amenable to problems involving sound, or natural language. You can think of each step as, for example, a word in a sentence. And so obviously, we would very much like to be able to design models to tackle problems like these. And the fully connected networks or convolutional networks from before, they will not really work because they expect your inputs to be a fixed size. And this thing can have an arbitrary length. So we need to find a way to deal with that. The key idea here, if we want to classify the sequence, is we want to summarize the input into some number of features. These features are the most important patterns for classifying it. So you can think of it like that. And we exploit the fact that there are relations between adjacent steps. We can process the input step by step. We take a function that takes the current step of the input and everything that the network has computed so far and produces the next set of features. And this function critically is shared. It's always the same function, and this allows us to process arbitrary sequence lengths. And this is why this is motivated by the fact that if we think something is interesting, it doesn't matter when it happens in the sequence. So we can use exactly the same function to detect interesting patterns no matter when they appear in the sequence. So the time step itself does not matter to what this function does. And a simple representation of this, a recurrent neural network cell, takes in the current step of the input and the previous set of features that were computed, and it gives you a new set of features which are also simultaneously fed back for the next step of the processing. And this is usually better visualized when we unroll it. So when it looks like this, we have a sequence of some number of time steps. And at each step, we take the current time step and the features computed so far, and we produce some new set of features. And we keep going on until we've fed the entire sequence into the model. And then these final features we can use for a classification by a traditional neural network. The key thing to remember here is that every single one of these blocks has exactly the same parameters, and they're all updated together using backpropagation. So this is the way in which we can process arbitrary amounts of data with the same number of parameters. Okay? Now, initial versions of these networks date from the 1980s, early 1990s, and they treat this RNN cell as a single fully connected neural network layer. But this has a huge problem, which is called the vanishing gradient problem. If we apply an activation function like the sigmoid, which has a derivative which is less than 1, and then you apply this gradient update at all the steps of your sequence, these gradients kind of multiply, 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 and when you multiply many things that are less than 1, you end up with something that very quickly approaches 0 as the sequence length grows, which means you cannot capture long-term dependencies. So say I want to predict the next word in a sentence, and I say, my name is Petar, I'm from Serbia, and then there is a huge paragraph of text, and then I live in blank. And the model should be able to say Serbia with high reliability, but because the gradient has vanished by the time it reaches the word Serbia, it's not able to actually figure out, it's not able to capture these long-term dependencies. So we need a model that is capable of working with something like this. And the first kind of popular model that solves this problem is the LSTM model that came out in 1997 from Hochreiter and Schmidhuber. And this cell explicitly learns from the data the proportion by which it forgets the results. So there are no vanishing effects like just from the network's design. You learn how much you want to vanish from data. And that's the key part. You learn how to forget. And several models have been proposed since then, some of which have been a bit more simple, some of which have been a bit more complicated, but none of them have really significantly improved on the LSTM on average. And this is just a rough schematic of how an LSTM works. So you might be computing new features the same way as before. You take your new time step, old features, but you don't just kind of take these features and move on. You control how much of the new features are let into the cell by this gating mechanism that says, based on my input and the previous features, how much of this input I want to remember. And you also have a memory cell out of which you control how much you want to forget. So you control how much you're forgetting from previous steps. And this is all learned explicitly directly from data. And that kind of solves implicitly the vanishing gradient problem. Unfortunately, I don't have a lot of time to focus on this one in detail. But what I want to highlight is that by now we've covered most or pretty much all of the essential architectures that are used nowadays across modern deep learning, and we're not even in the 21st century yet. So it turns out that we knew a lot of this stuff all along, but several key factors were missing. And those factors are, well, we needed better hardware to run these models on, so we needed some demanding gamers to push GPU development. We needed big companies to have lots of resources and to be able to create deep learning frameworks for us to use and simplify prototyping. And we needed big data to be able to fit these big models that have millions of parameters. So what's exactly new methodologically? Well, some examples of what's new. Previously, training has been done in a batched fashion in the sense that you will accumulate these gradients for gradient descent across your entire training set. And for big data sets, this simply does not work because it can not only be remarkably expensive to compute for one time step, it may not even fit, your data set may not even fit in memory. You might not be able to compute this many gradients at once. So the solution to this is actually quite simple. Well, the simplest solution you can think of this is rather than taking all of my training examples at once to estimate the gradient, which is kind of the most precise thing you can do, just take one of them. So take an example at random and just compute the gradient based on one example and just keep doing that. That is the essence of stochastic gradient descent, which has revolutionized the way deep learning is done. And, well, you might think that estimating a gradient based on one example is just a bit too noisy. What if this example is a bad one and it kind of throws you off? So in practice, we use the golden middle approach, which is we take a small set of examples called a mini batch, and we train based on that mini batch. This is the mini batch stochastic gradient descent, which is pretty much ubiquitously used nowadays in deep learning. And what's also nice is that recently there have been a variety of methods that automatically estimate the optimal choice of the learning rate for us, which used to be quite a major problem to properly tune this parameter. Now we have techniques like ADAM or RMS-prop that you can directly plug into your network and they just do all the work for you. You don't have to worry about how big steps am I taking in the direction of my gradient. Now, as we get deeper and deeper, the problem that we had with vanishing gradients from before, from the LSTMs, they strike again. But we cannot really reuse the LSTM ideas like the gates and stuff. We cannot reuse them in feed-forward networks. The solution is use a different function. Use one that does not have a vanishing gradient. And this was one of the inspirations behind the ReLU function, which is a very simple way of introducing nonlinearity into a model. Just say, if it's less than 0, set it to 0. So it has a shape like this. And its gradient is exactly 1 when it's active and 0 when it's dead, which means there is absolutely no vanishing that you need to worry about. And it's first been deployed by Nair and Hinton in 2010, and now it's pretty much ubiquitous across deep learning architectures. Well, variants of this function are now ubiquitous across deep learning architectures. And there have also been some relationships between what this function is doing and how actual neurons conduct electricity in the brain. Okay, so also, we have developed techniques to help the models regularize better, as in fit not that big data sets using a huge number of parameters. Now, if you are not familiar with the concept of overfitting, I always like to introduce it using this example. Say I want to learn a sine function based on some training examples, these blue points, and I've extracted them with some noise present, so these points don't exactly follow the sine function. I first start by approximating it by a line, and it's not very good. Then I try a polynomial of degree 3, and it seems to work quite well. And then my colleague says, but wait, I have 15 points in my training set. If I take a polynomial of degree 14, I can fit it perfectly. And he produces this function, which indeed fits my training set perfectly, but the moment you stray a little bit from the training set, your results are horrible. So this, in my opinion, perfectly illustrates the concept of overfitting in the sense of you're throwing too many degrees of freedom at too small a number of examples, and it inherently learns all the noise in your examples. And this is a very small example with 15 parameters. Neural networks have millions of parameters, and this image is infinitely more, well, not infinitely, but hugely more dimensional. Okay, so some techniques that are kind of black magic and work really well when it comes to regularizing models. One of them is Dropout, which is actually, at first glance, it might not seem like a sensible idea. While you're training, you just randomly take some neurons and you kill them. They're not part of your network anymore during this training step. And the reason why that actually works really well is because one common way in which a network can overfit is that one neuron learns to do all the work in a layer and other neurons are just sitting there being useless. Or even worse, one neuron learns to behave really badly and then you have 2 or 3 neurons there just to correct it. So if one neuron then misbehaves, the whole network kind of crashes down. So when you're forcing the network to not rely on an existence of a neuron, you're effectively teaching it to learn a consensus of neurons. They have to learn how to cooperate in some way. They have to learn more robust representations. And this is why Dropout actually performs as well as it does. And another concept that I'm really surprised it took us until 2015 to discover this concept, but it's revolutionized the way deeper networks are trained nowadays, is there was a huge issue with training deeper networks in the sense that even though you normalize your inputs nicely at the input layer, by the time you go somewhere in the middle of the network, the statistics of the signal have completely changed. The mean might have changed, the variance might have completely changed, and that means that a gradient update that works somewhere in here might not propagate nicely to the shallower layers, and your network is no longer efficiently learning. So how did we solve this? Very simple. We just, at each step, well, whenever we care about somewhere in the middle of the network, we renormalize all of our inputs. So we take the mean and we take the standard deviation from all the activations in the network so far, and we renormalize them. Yeah? And this gives us the batch normalization algorithm. One minor detail is that when you do this normalization, you effectively limit a little bit the capabilities of your network. So just to allow the network to go back if it thinks by normalizing we've done a bad thing, after you've done the normalization, you apply a learnable scale and shift to the inputs, and this effectively allows the network to go back if it thinks that the normalization has done something wrong. And you can also think about it as the network learning its own normalization. And now it's ubiquitously used across deeper networks. These are actually quite old slides. This does not have 1,500 citations by now. It has more than 2,500. So this is a technique that's pretty much used everywhere in deep networks right now. And OK, how am I doing for time? How much do we? Yeah, great. So I want to show you now a few examples of what deep learning has become good at and some of the pressing challenges in the field. So one of the first success stories on image tasks was actually with classifying traffic signs. This was the first time a convolutional neural network architecture was able to outperform a human performance on a particular task. And I hope you can see what I mean when I say outperform human performance. If you look at some of these signs, the brightness might be really messed up and might be actually really hard for you to see what's the traffic sign that I'm looking at. And a neural network is actually capable of distinguishing, even in those circumstances, better than a human in a lot of occasions. And this is, I hope you can clearly see why this task is of huge importance if you want to build a self-driving car, for example. Because it's really important for me to be able to know what road sign am I looking at to be able to appropriately adjust speed or something like this. So this was the first major success story of convolutional neural networks. Then obviously in 2012 was the first time that deep convolutional neural networks were placed against traditional methods at the ImageNet classification task, which is a 1,000-class classification problem. And it's really hard in the sense that you have to simultaneously be able to distinguish like 100 different breeds of dogs, and you also have to be able to detect different kinds of plants, different kinds of objects, kinds of cars, and so on and so forth. So a network that performs really well at ImageNet is something that is a method that's generally really good at extracting deep features from images, generally speaking. And 2012 was the first time that a deep convolutional neural network was deployed on this task by the team at University of Toronto. And they have been able to achieve results that significantly outperformed the next best method. And before we knew it, all the methods were convolutional neural networks. And in 2015, Microsoft Research was capable of exceeding human performance even at this task with a 152-layer residual network. And here you can see, obviously, because this task is really hard and sometimes the correct answer is not even obvious, the network is allowed to make 5 guesses out of the 1,000 classes. And if the correct answer is in any of those 5, then we conclude it to be correct. So sometimes it makes the correct answer. Sometimes it makes the answer which could be correct based on the way I'm looking at this image. This could have been a convertible. And also, this one is my favorite example. The network says that this is a Dalmatian with high confidence. The correct label is cherry. But I mean, I hope that you can see that the network is not really wrong in this case. It's just that sometimes it's really hard for the annotators to agree amongst each other as to what the correct label is. So even when the network is wrong, it might have some useful insights that can be seen. Okay? You can then take something like this, something that takes an image and gives you a class, and apply it for really simple kinds of navigation. So there was this project where a drone was looking at a particular region of an image, and they were classifying based on what I'm looking at, should I go left, right, or keep going forward? And just based on this 3-way classification problem, the drone has learned how to navigate trails, which is a fairly important thing to do if you need to, for whatever reason, patrol those trails. And you can then take this to the largest possible scale with autonomous self-driving vehicles that have to be capable of doing many different things on the image that they're looking at right now. So they have to be able to identify what are the objects of interest, like take bounding boxes of these objects, what kind of objects they are, and how fast they're moving, which is also quite critical. And one thing that's interesting about these systems is you can train them from many hours of people just driving on the road. But recently, they've also been trained by using video games, such as GTA 5, which have reached sufficient levels of visual complexity to enable something like this to happen. Okay, now I'm not a speech person. This is a disclaimer. I don't do lots of language or speech kinds of problems, but I had to give at least one example that dealt with sound. And this was my favorite, the greatest hits data set and the associated method, which looks at a video and tries to synthesize the sound. So basically, they took a drumstick, and in their data set, they kind of hit this drumstick across different surfaces, and the network was supposed to predict what's the sound that the drumstick makes when it hits the surface. And it gives some really interesting results and also some really interesting failure cases. But I thought that this, the sound synthesis based on video is one really exciting application of recurrent models that I've been able to see. Then you have the famous example of neural style transfer, which allows you to take a style from a particular image and apply it to a content image. So preserving content while transferring style. And the photo on the right actually comes from a previous Cambridge Spark workshop. And you can see the difference between the original image and the style of Heisenberg, which is applied to the right side of the image. And the way in which this is done is by a custom loss function that allows you to modify, because the same way the weights were differentiable in a network, you can also differentiate with respect to your inputs. So you can tweak your inputs to make the network that's pre-trained produce something that you care about. In this case, what you care about is preserving the content that was in the original image. This is easily quantifiable as a combination of loss functions. And also something that captures the style of an underlying image that you want to transfer. Okay, another really exciting example is Neural Talk. This is a very impressive video. You can look it up on Vimeo later, where someone is basically walking around the city with a camera, and as the person is walking, the algorithm is captioning what's going on in the scene. This is a combination of convolutional and recurrent neural networks at work. Convolutional network to process the image, extract features from the image, and a recurrent network to generate sentences based on what it's looking at. And just so that you don't think that it's as impressive as it might look, this is a very impressive cherry-picked example, but I've seen really, really funny mistakes of these captioning applications. For example, a person riding a horse, that's my favorite, and the network generates a horse riding a horse. So these networks are sometimes like, clearly they see what's going on, but not always coherently explaining what they're looking at. And perhaps my personally favorite example is neural networks have, for a while already, been a state-of-the-art approach to automatically playing different old-school Atari games, which was first popularized by deep Q networks and is now like a very heavily growing area of reinforcement learning, which which operates on a variety of different platforms nowadays. But what's key about this is that even though DeepMind originally wrote this as a system that plays games, they have afterwards been able to make advantage of it and deploy it within Google's data centers. So the same kind of system that learns to play the game just by knowing the rules and taking actions and observing rewards it gets, they've applied this to control the cooling systems in Google's data centers. And according to their blog post, this same kind of algorithm was able to decrease Google's power bill by 40%, which pretty much paid off the entire cost of acquiring DeepMind in the first place. Okay, now a few challenges for the future and some ways in which we might be addressing those. So one huge challenge right now is that we've kind of built these custom models that work on a particular kind of input data. So we have convolutional networks for images, recurrent networks for sequences, fully connected networks for just sets of features. But what if I want to combine different kinds of inputs? Because often I have inputs of many different kinds. If I want to classify based on a video of a person saying something, I need to have something that works simultaneously with audio and with video. And currently there is a lot of work towards this, but there's a lot of unsolved challenges that allow us to create scalable models of this kind. And actually, my research group and members of my research group are actively working on some problems in this space, because in biology, which is what we focus on a lot, you often get different kinds of data that are highly differently structured. You can have medical images, you can have genetic measurements, you can have a lot of different things that have a lot of different dimensionalities, and properly integrating these represents still a major challenge with a lot of work to be done. Then one huge, well, Jan LeCun called it one of the biggest challenges of machine learning at this time is the challenge of unsupervised learning, so learning without labels, because most of the data you see is without labels, and arguably the most pure learning is unsupervised learning, in the sense that how do you learn that something is a cat or something is an A character? Presumably the first few times someone showed you a cat and said, oh look, this is a cat, but then in the next several years of your life you've seen many cats and no one was really behind you to tell you, oh look, this is a cat. So you might have started with some small levels of supervision, but in essence, most of the learning that humans do in life is unsupervised. So we really, really want to be able to capture the way learning is performed when we don't have explicit labels. And currently, the most exciting approach towards doing unsupervised learning is doubtlessly the approach of generative adversarial networks, with two networks playing a game. So you have the set of your true training set of images or any other inputs, and you train a network to be able to generate fake inputs. If you're able to generate things that look like they came from your training data, in a way you understand your data. So this generator has to learn how to generate new examples from some randomized inputs. And then we have a second network that takes an image or any input and tells you, has this thing came from my true data set or has it been generated by this counterfeiter? And these two networks are at constant odds. They start with random parameters and they're playing a game against each other. And the hope is, if you train them nicely enough, this is a huge open problem how to properly train these things, you end up with a really good network that really nicely discriminates things, so it captures really nice features about the data, and you have a network that's capable of capturing really complex things about generating the data. So you get two really useful networks, and this is a very, very exciting approach, but very, very unstable, and there's a lot of work to be done. A lot of work to be done to make this one work properly. And finally, potentially the most important challenge if you want to kind of move towards a singularity or whatever it is that Elon Musk wants to scare us into thinking, is all the networks so far, and all the networks I've talked about thus far, have been kind of specialized to do one task. You do one task, and then you throw away the network. So when you want to do something else, you basically just have to start over again, and there's very few things you can do to overcome this phenomenon of catastrophic forgetting. So you might learn to specialize for something else, but in the process you completely forget what you've learned before. And there's been a small number of steps already done towards ameliorating this problem, and one of the approaches I like that came out in the past 2 years is the approach of progressive neural networks that came out from DeepMind. So they first train a neural network to learn how to do one task, and then they want to teach another network to do a second task, but they can reuse the features. So what they do is they freeze the first network, and then they use it to extract additional features which are fed into the second network while the second network is training. And this actually allows the second network to learn much faster. For example, if I want to learn Pong and to learn how to play Pong and how to play Breakout, in both of those games you have a ball that's bouncing off of a paddle, so clearly there are features across the two tasks that are interchangeable. So having a network like this that first learned how to play Pong and then using its features to learn how to play Breakout can actually speed up training of the second network a lot. And in the robotics domain, they've actually been able to observe much more impressive improvements of up to 30 times the training, less training time. And obviously this thing still has shortcomings. For each new task, I need to create a new network, so this clearly does not scale in terms of memory. And also, knowledge only flows in one direction. There's no way to use the knowledge from new tasks to help old tasks learn better. So clearly there's a lot of work to be done in this direction, but it's just so you know that there is work currently being done, and this is one of the major challenges, in my opinion, of today. Okay, so this actually concludes my talk for today. If you have any questions, you can, well, feel free to ask them now, or you can contact me via email. Okay, thank you.
Any questions for Petar? I will make sure we give you the microphone.
Just wanted to ask how significant you think ladder networks are and the role of attention.
Okay. So the last time I gave a talk like this, I was also asked about attention. So this is, once again, the bias of me not working in sequential models. But I have had a chance to work with the group in Montreal over the last summer, and a lot of them are really actively working on developing attentional models. And in my opinion, the value of those models is, among other things, interpretability, because you're able to tell exactly what parts of my input were important for making the current prediction, which I think is a very important step towards understanding how these networks work in general. And obviously they're able to, the recent self-attention paper that came out of Google Brain was also quite impressive, showing that just with attention, so without any inherent structure assumed in the data, we can outperform state-of-the-art on machine translation. So I think it's definitely a very important step, and I think that maybe in an optimal, ideal world, we wouldn't need recurrent networks for anything because they are very computationally expensive. because they're inherently sequential. You have to process the inputs step by step, and this incurs a cost that you cannot really parallelize with GPUs. So in my opinion, it's a very promising direction, and we should definitely be advancing more towards this, and it's very important. The reason why I didn't include it here is simply because of the bias of the things that I work on in particular. And while I haven't had a chance to work with ladder networks personally, I have heard sufficient buzz about them that I think that they're also a very, very important direction. Yeah. Thank you. Yes?
So one of the problems with adversarial attacks that you have add a little bit of noise and then get it to incorrectly classify, for example, a catalog.
Right.
How do you think?
So adversarial techniques, yeah.
Yeah.
So the general problem of this is that when you are training to learn any model, not just a neural network, you are capturing underlying statistics in the training set that you have. So anything that significantly deviates from those statistics is something that the network simply is not expecting to see. So there was a famous example recently where the MNIST digits, if you invert the black and white colors, the network completely fails because it's not used to the fact that the digits are supposed to be white and not black, or vice versa. So this is a very simple way to say that if a network is not used to seeing something, then it's going to underperform on it. So what happens with adversarial examples is actually there is an entire space of adversarial examples where you just slightly perturb an image and you make the network completely confused. It's because you can use really small variations of pixels, variations that are maybe often imperceptible to the human eye, to kind of embed a pattern within an image, if that makes sense. So you're kind of embedding a pattern of something else within your image, but you've done it with such subtlety that the network still, that the human would still think it's looking at a panda and not at a gibbon, for example. So the reason why this works is because by modifying the image slightly, you're exposing an image to the network of the kind of statistics that it's not used to seeing. And that's, I think that's the core cause of where the problem is coming from. And unfortunately, I don't know of a good way to kind of properly deal with these problems in the context of security other than just anticipating what are the kinds of attacks people might do on you and augmenting your training set appropriately.